Hello folks, this is Todd Coburn of Cal Poly Pomona with Lecture 4 of Aero 3271. Today we're going to be continuing our study into fatigue, and we're going to focus on the endurance limit. We already learned about the endurance limit. We're going to back up, review what we did, and then extend what we did to cover more types of things we might see. So remember, we looked at this chart last time where we see that if you plot the endurance limit of various parts versus the tension strength of material, we find roughly a linear relationship up to about 100 KSI for steels. This gives us the relationship that we can estimate the endurance limit from the tensile strength. Now, what that does, we said then that S sub B, the endurance limit, was equal to that fraction. Now, if we look at other materials and plot the tensile strength against the endurance limit, we already saw a different curve for steels, like the one shown upper left here. We have this, if we have a wrought or a cast iron, we're going to get a relationship like this one below it. And over here to the upper right, we have aluminum alloys, and then below that, copper alloys. Now, you'll notice for these curves, they have also plotted these as a function of the fatigue ratio, or the minimum or the maximum stress. So we find out that it may not only be a function of tension strength, that the fatigue ratio may also be a parameter. But we're going to ignore that for now and just use the approximation of what this average curve relationship gives us. We're going to use this information to come up with our first estimate of the endurance limit. And remember, we're going to call this the S sub B prime, the pristine, perfect endurance limit for that material if the samples were round, rotating, fully reversed stresses, polished samples. Once we understand how to calculate accurate, pristine S sub B primes, then we will go and learn to modify it for other materials, as we're going to do here. So what that brings us to, if we study that data and collect the data of others, we get this relationship shown here in this table. We see that steels, as we saw last time, we can approximate the endurance limit as about 50% of the ultimate strength of the material, with a cutoff, which means we're not going to go above 100 KSI. So all we got to do is look up what's the FTU of the material we have. We're going to calculate 50% of FTU. If that's less than or equal to 100 KSI, we're going to use that. If it's more than 100 KSI, we're going to imagine that it's just 100 KSI. Irons, and actually everything else, irons, aluminums, titaniums, and coppers, we're going to assume that that relationship, that S sub B prime is 40% of FTU. We'll see we got a cutoff for iron and for aluminum and for copper, but not for titanium. That means titanium, we're just going to use whatever value it gets to. This is one of the most common errors that students make, is when they're using the endurance limit, they use the pristine value without paying attention to the cutoff at 19 KSI. 40% of FTU will come up with more than a 19 KSI for many materials, or for many parts you will see, and we're not going to use anything greater than 19 KSI for aluminum. Got it? Now that we understand the pristine, perfect endurance limit for the material, S sub E prime, we can begin to change that perfect, pristine endurance limit into something that more accurately represents how our part will behave. Things like the surface finish, and the loading, and the temperature, and those kind of factors can affect the endurance limit, as well as how careful do we want to be? How much reliability do you want our answer? How close do we want to get? Since we have scatter with all data, that means any value we use has a chance of being wrong. And if we want to reduce the chance of being wrong, we can use a higher reliability, which doesn't change how the material behaves, but it changes how much credit we're going to give for how the material behaves. So let's take a look at that. And then what we're going to do, once we collect these factors, and the way we do this, we're going to find out for each effect, we're going to come up with a mod factor we'll call K. Those mod factors, Ka, Kb, these are called Marin factors because he's the guy that developed how these factors are applied or came up with this approach. So we're going to come up with a factor for each and every one of these effects that might apply, and we're just going to smack them up against our pristine, perfect endurance limit to calculate what the endurance limit is for our part. And that's how we're going to do it. So you'll notice we're going to take our S sub B prime just from FTU and the cutoff value, and then we're going to apply our Marin factors. When we're done with that, we will have the endurance limit, which will be our best estimate of how that material will behave. So the first Marin factor we're going to use is called the surface factor. This draws attention to the idea that if there's an issue with the surface, like a rough surface is going to be more prone to fatigue failures because of crack initiation sites than a nice smooth surface. The way we're going to do this is come up with this relationship. They have found that although the FTU doesn't have any effect on the surface, the FTU can affect how resilient that structure is. Actually, it's more a function of the hardness, but we can often, since hardness is related to FTU, you can factor that as FTU. That's what they've done. And we come up with this equation, K sub A, that Marin factor for the surface condition can be just an A coefficient, a B slope, and our FTU. SUT is just the FTU of the material, another word for it. And we see in this table here that different surfaces will have different A and B factors. So a rough surface, like from a ground operation, will have a different effect than a machine surface. Now, due to uncertainties in choosing which surface finish is appropriate for our particular part, to keep things simple, in our class, we're just going to assume that the machine and cold drawn surface condition applies unless there's something in the problem that says it's an as rolled, hot rolled, or an as forged, or something like that condition. Got it? Okay. So that means we're going to be using an A of 2.7 and a B of minus 0.265 in this equation here for most of our parts. Okay. Second Marin factor is the size factor. The larger a material is, the more chance of, the more of the area that may be affected. So if we have let's say we have a round sample and we have bending or torsional loads, then we will have these two equations. If our diameter is less than or equal to 2 inch, we will use the first equation. If it's greater than 2 inch, we'll use the second equation. You see that? Now you'll notice it has diameter being greater than this. That's really the effective diameter is greater than this, or if it's less than this, right? And that D sub E, that effective diameter, what that means is if the sample is round, then obviously the effective diameter is the actual diameter. We're going to find out if the sample is square or I section or something else. We can come up with an effective diameter, which we will then plug into this equation and check the part. Got it? So if we have a round rotating sample, these equations apply. If we have an axial load, we're going to use K sub B equals 1. Now this is just an excerpt from your handbook. The first part of this is just a repeat of what we saw on the other slide. So if you roll down a little bit, we're going to see that if we have a round and non-rotating part, we're going to use equation 444. Now it may not still be the same number equation in your handbook, but basically D sub E equals 0.37D. And if it's rectangular and non-rotating, we're going to use that next equation, 0.808 square root of HB, where H is the height and B is the width of the part. Got it? What if we have a more complicated section? That brings us to the next slide. So if we have a round rotating sample, then we have this first equation, 2 square root of HB over pi. If we have an I section that's not rotating, we're going to use these two equations. Now what we've got to do is look first, what direction is the loading? If the direction is causing bending about the XX axis, then the first equation applies. If it's about the YY axis, then the second equation applies. Now if you turn your H section, you've got your H section, and you turn it on its side. Now to be associated with this picture, the x-axis is going like this. So we're talking about that bending for the first equation, this bending for the second equation. So be sure that doesn't trip you up. If you have a C-section, once again, you have to pay attention to the axis and the orientation. If your C-section is like this is the x-axis. Bending about that axis, use the first equation. Bending about the other axis, use the second equation. If you use your sample like this, then the x-axis, according to the picture, is actually vertical, and that means the first equation is for this kind of bending. Don't make that mistake. Also, another trick here is you'll notice that y-bar is in the equation. You need to make sure that the y-bar is defined in the same way as the picture. If you define y-bar from the lower open flange rather than from the up where the elbow is, then your answers will be wrong. Got it? Our next Marin factor is the loading factor. What this says is different loadings have a different effect. And if we have bending load, since this whole process was based on bending, then our factor is 1. If we have axial load, our factor is 0.85. If we have torsion, our factor is 0.59. Okay? Next factor is the temperature factor. Now, what happens here is if you have a curve like what's shown here, where we know what the strength of the material is, this leftmost curve shows the strength of, what is it, AISI low alloy steels as a function of temperature. Now the way this curve works, we can see we have FTU and we have FTY in the equation. Now in fatigue, we're mostly using the FTU for all of our parameters, so we're going to use that upper curve. And you notice that this is percentage of room temperature strength. So what we would do is go and look up the FTU of the material from the back of our handbook. Then we would come here, take the temperature, go on the horizontal axis to what the temperature is, and then read whatever the knockdown factor is. What this says is you're somewhere between 80% or 100% and like, what, 35-ish% or something of the material. So you'd multiply your FTU by whatever factor, 0.35 or 0.85 or whatever, according to your curve. Okay? Here's a corresponding graph for 7075 T6. You'll notice we have a number of temperatures shown. If we want to be conservative, we could go and use that lowermost curve, but try and think about when do you ever have a part that's loaded for 10,000 hours at a certain temperature. Not on an aircraft. There are no aircrafts flying for 10,000 hours that I know of, right? So what we generally do, mostly our loading will be low, our time of load of that temperature will be lower, and we use one of those upper curves. In our class, we'll just use the uppermost curve for estimating the strength knockdown. If we do use that approach, all we got to do is we can use whatever that room temperature strength. If we read the chart and we find that it's 85%, then our K sub D is just 0.85. If we read that it's 100%, then we find out our K sub D is just 1. If we have a 30% strength at that temperature, that means our factor is 0.3. Got it? Now, if you're actually instead given the allowable at temperature and the allowable at room temperature, you can then develop your own factor by just taking the ratio of those factors. You take the at temperature that it's going to be at divided by the room temperature net strength, and that will give you your K sub D. Okay? So this is the reliability factor. The next one is, since there's scatter in this data, and you notice that basically in this curve, there's about half the samples fail below the curve and about half of them fail above the curve. This means that this is associated. If we use that 50% knockdown, that's about a 50% reliability. And if that means if we have if you want a 50% reliability, then our reliability factor is 1.0. If we want a higher reliability, we're going to have to go and read this curve, this table, to find out what factor to apply. And it's useful to note, if I tell you to use a B basis kind of reliability, that we need a B basis knockdown, then you will go and read the B basis, which would be a 90% reliability, or an A basis, which would be more like a 99-ish%. Okay? That's how we're going to handle that. Here is some, the one more Marin factor, the miscellaneous effects factor. Actually, this is always going to be one for us. What this basically says is if you have an idea, some epiphany that makes you think that maybe the color of the t-shirt you're wearing when you're doing your loading your sample affects the part, or maybe the love with which the part was constructed affects it, you could go and try and do testing to find out what that factor was and add a new factor for your little pet idea of what might affect fatigue strength. For our purposes, this is just warning us that there may be other factors that some folks may come up with or that you may come up with. We're going to just assume this is 1, which basically means we can drop K sub F out of our calculation. Often, many of our factors will be 1. So we're going to read the problem carefully. If there's no evidence in the problem that a certain factor is appropriate, then we're just going to assume that factor is 1. If there's any indication from the problem statement that one of these other factors, maybe the reliability is wanted at a different level or the part has a certain size, then we will go and try and calculate what those factors are. Okay? The next idea is stress concentration. Now, we learned about stress concentration before. We used that idea of K sub T, the theoretical stress concentration. And in order to calculate that, we went to Appendix C of our handbook and looked up the appropriate geometry and loading to get what that is. Now, in fatigue, basically the same stress concentration factors are valid. However, it's been found that fatigue, some materials will not react as poorly to the stress concentration as a static loading. A fatigue loading sometimes is not as bad as a static loading for purposes of stress concentration. So what we're going to do, if we have a stress concentration, we will calculate the K sub T in the normal fashion, and then we will modify it into a K sub F, a stress concentration factor for fatigue. Got it? The way we're going to do that is through what's called the Neuber equation. So this is how the Neuber equation is defined up above, but the way we're going to calculate it is usually not using this upper equation. What we're going to do first is figure out what the square root of a term is in this lowermost equation. So if you look down below, we're going to see if the loading is in bending or axial load. Then we'll take FTU and we'll plug it into that first polynomial. If the loading is torsional, then we will plug in FTU into the second equation. You'll notice this doesn't give us A, it gives us the square root of A. So don't make the mistake of now taking the square root again of that factor. Once you get that number, you're going to take whatever you come up with, that square root of A term, plug it into this equation for Q, as along with the square root of the radius of the feature to calculate your Neuber equation, to calculate this Q, the notch sensitivity, which we're going to call Q. Don't confuse this with running load, the shear running load Q. This is Q, the notch sensitivity factor. Once we have the notch sensitivity factor, we'll plug it into this middlemost equation, multiply it by K sub T minus 1 plus 1, and that gives us K sub F. Okay? Now, once we have our notch sensitivity, what we're going to do is plug it into this middlemost equation and calculate our K sub F. If we have a Q of, let's say, 0, what that means is your K sub F is going to be 1, regardless of what your K sub T was. This means that for that material, the notch will have no effect of hurting the stress, and we'll just have our regular net stress. If you have a Q of 1, in that case, we'll find that the whole notch sensitivity, you're going to end up finding that K sub F is equal to K sub T, and the material behaves just like a static part for purposes of stress concentration. Okay? And we will use a notch sensitivity of 0.2 for cast irons. There's a little explanation of why there. Let's try a couple conceptual questions for a minute. Let's say that a part is loaded repeatedly and it looks like it's loaded like this, with bending going like this. What's the load factor K sub C? Well, if you look at your handbook, it's 1, because the loading already looks like fully reverse bending, doesn't it? If our repeated load is instead tension compression, axial tension and compression, what's our factor? That's right, 0.85. What's the endurance limit for pure titanium parts? Remember, we're going to start with a pristine perfect value of 0.4 FTU. What is the endurance limit for 6A L-04V titanium parts? Well, this is another titanium, same thing. Somebody goes and gives you a test problem and gives you all kinds of information, but you can't say anything in the problem about what reliability is desired. So what reliability factor should you use? That's right. If there's no other information, we're going to use a case of E of 1. What reliability does this value correspond with? 50%. Remember, we had the curve, and that 50% factor was based on the average. We had data below it and data above it, and it looks like it's roughly about the same amount of data on each side. Is that conservative? No, that's not conservative, but sometimes done. Would you fly on a plane if you knew some parts had a reliability factor, had 50% reliability? 50%. Would you? Okay, so let's just give an example to think about that. Let's say aircraft A has a 50% reliability on all fatigue analysis. Another aircraft has a 99.999% reliability. But aircraft B, due to the difference in calculation, costs $500 more per ticket. Which aircraft would you book on for your flight to Disneyland, Florida? Think about that. I don't believe it. So let's say we have a part like this, loaded in fully reverse tension compression. What steps do we use to calculate the stress? Right? Calculate our net stress, net area, net stress, stress concentration factor, not sensitivity factor, K sub F, apply that to the stress. Right? How can I ace this miserable class? Which one do you think? That's right. All right. That's all I got for you. Enjoy.